So far so good, amusing but perhaps not of so much moment. After all, we have seen decimal expansions very early on in our mathematical experience, and this is just a binary or a dyadic expansion along the same lines. But here's where it might strike a chord in our memory. Where have I seen such expansions before in a different context? Aha! Didn't I see such expansions as the outcomes of my idealized chance experiment in tossing a coin repeatedly without end? This suggests now that there's a connection between these number-theoretic ideas in the representations of real numbers and the sample points of my idealized coin-tossing experiment. This allows us to complete the loop triumphantly. Recall again, the experiment is as follows. We toss a coin repeatedly. By the identification of a head with the number 1 and a tail with the number 0, the sample points of the experiment are infinite sequences of 1s and 0s. But every such infinite sequence, x1, x2, x3 of 1s and 0s, corresponds to a real number x in its dyadic expansion, and therefore to each such sequence I could allocate a real number x. This number x is a value between 0 and 1, and in a more compact usual notation we will write this as simply the unit interval 0 to 1 enclosed in square brackets. Now, we just restated the problem through this beautiful correspondence with numbers. And we've certainly got a very compact representation, the unit interval. This coin-tossing experiment can be identified with the unit interval on the real line. Isn't that surprising? Isn't that beautiful? Now, the moment we've got such a compact representation, other things start falling into place. What can I say about the event A that the first head occurred on the fourth toss? Well, it's all binary strings where the first 3 elements are 0, the fourth element is a 1, and the remaining elements are arbitrary. Now, what does that mean? It means I'm looking at numbers with a decimal point followed by 3 zeros, 1, followed by what? Well, at one end of the spectrum, I could imagine followed by a sequence of tails, an infinite sequence of tails. In our new language, that corresponds to the sample point 0, 0, 0, 1, and zeros repeated ad infinitum. Okay, that gives me a bona fide x, which is in my A. At the other end of the spectrum, I could start the sequence with a 0, 0, 0, 1, and follow it with an infinity of heads, in other words, repeating 1s. Now I notice that the binary numbers, the x corresponding to each of these, is at 2 ends of a spectrum. All other sample points in A, starting with 0, 0, 0, 1, followed by some sequence of zeros and ones, will lie in between these two extremes. And therefore, I can identify A very compactly. A is equivalent to the set of real numbers x, which are such that their dyadic expansions of x lie between two extremes. On the left, point 0, 0, 0, 1 recurring zeros. On the right, point 0, 0, 0, 1 recurring ones. And it's clear that any other possibility for the fifth toss onwards will give me a number in between them. Oh, this is nice. Okay, now I've got a compact representation for what this means. But the notation, 0.0010 recurring, 0.0011 recurring, is a little mysterious. We should dig out and see what does this actually mean. So let's start with the left-hand side. 0.0010 recurring is just a short form for 2 to the power minus 4, or 1/16. Easy. What about the next one? Pause and write it down and see if the dyadic expansion rings a bell before you proceed. Did you discover this? Writing down 0.0001 with 1 recurring just means in the dyadic expansion 2 to the power minus 4 plus 2 to the power minus 5 plus 2 to the power minus 6 and so on ad infinitum. But again we discover our old friend, the geometric series. This sums to, in the numerator 2 to the power minus 4, in the denominator 1 minus 2 to the power minus 1. In the numerator I get 1 over 16, in the denominator I get 1 over 2, the ratio then gives me 1 over 8. And I've discovered really a beautiful, magnificent description of the event A that the first head occurs on the fourth toss. It corresponds to all real numbers sandwiched in the interval from 1/16 on one side to 1/8 on the other. Or, in the compact notation that we are used to, it is just the closed interval from 1/16 to 1/8. Oh, we can't ask for a much more beautiful and compact representation of this apparently abstruse problem. Now, we could proceed from here directly, but in a setting like this, some geometrical attributes make things really vivid. A picture, as they say, is worth 1,000 words. What are we dealing with here? We are dealing with the unit interval on the real line. Let's plot this. Now, in that unit interval, that's a segment of a line. We are looking at a subinterval. That subinterval starts at the point 1/16 on the left and proceeds to the right to the point 1/8. This is a continuum of real values. Any point in this continuum of real values corresponds via our dictionary of translation, via the dyadic expansion, to a particular sequence of heads and tails, and therefore corresponds to a sample point in the underlying experiment. We should very quickly test this out, okay? So, what is another example of a point somewhere between the two extremes? Well, perhaps I could say, well, I have 3 tails, a head, and a head immediately after that, followed by an infinite string of tails. Now, what does that mean? Well, that means we have the number 0.0001, followed by a recurring sequence of zeros. Of course, this just means 2 to the power minus 4 plus 2 to the power minus 5. And we say, oh yeah, this is easy, I get this. And this gives me a point which is exactly at the center of the interval. This is one such sample point. Of course, you could imagine, let your fancy play loose here. You could imagine any sequence of zeros and ones following the 1 in the 4th place. And any such sequence will give me a point, a real number somewhere in that interval. Oh, this is beautiful, this is elegant. We really couldn't ask for more. But we do. Right? How does one go about constructing a probability measure? Well, the moment one has constructed such a simple and elegant representation for the problem, then the construction of the measure becomes not trite, perhaps, but perhaps evident. Well, let's take a look here. Remember, the points in the unit interval represent infinite strings of coin tosses, but the coin is assumed to be fair, and therefore all strings are statistically identical. There's no reason for one to be favored over the other. Another way of thinking about this is this. If you take a string of heads and tails, and you swap the heads with tails and tails with heads, then you'll get new strings which have the same character from a statistical point of view. Heads and tails are equally likely in this experiment. Another way of thinking about this is we want to appeal to symmetry. If you look at all the sequences in the first quartile of the unit interval, they correspond to certain sequences of heads and tails. If you simply replace heads by tails and tails by heads, replace ones by zeros and zeros by ones, you end up with a corresponding quartile at the right end of your unit interval. And therefore, this is another way of saying the first quartile by symmetry should be as likely as the last quartile. In fact, any quartile should have the same chance, and all of these should have the chance 1 in 4. Generalizing very quickly based on this idea, we say that the probability of any interval must in fact be proportional to the length of that interval. A quartile, an interval of length 1/4, must have a chance 1/4. An interval of length 1/2, wherever positioned, should have a chance of 1/2. An interval of length 1/16, wherever positioned, should have chance 1/16. And immediately, this gives us now a probability measure. The probability of the particular event A, that the first head occurred at the fourth toss, corresponds to the length of the interval from 1/16 to 1/8. And the length is 1/8 minus 1/16, or 1 in 16. We now have a formulation which allows us to compute probabilities in a principled and systematic way. This procedure satisfies positivity tritely because length is positive. It satisfies normalization. The unit interval in this case has got length 1, probability 1. And additivity is trite because length is additive. The length of two disjoint pieces is the sum of the two lengths. And now we have a procedure which allows us in principle to move beyond the setting of the discrete space and to move into continuous spaces. To summarize, what have we discovered here? First, we have discovered, against the odds, from a coin-tossing experiment, admittedly a conceptual coin-tossing experiment, a continuous sample space. The outcomes conceptual of this experiment take on a continuum of real values, in this case, in the unit interval. The basic events of interest here are naturally intervals. Intervals are the fundamental units in the continuum. And how do we allocate mass or probability to intervals? Well, we simply make it, in this instance, proportional to the length of that interval.